Cool. Hi, everyone. Hi, Dan. I'm basically Neha, and I work as a product manager with Ori. Being a PM, I'm always curious, talking to my customers and basically picking from their experiences. I believe the great products need intuition, and to build them, that's the way for me going forward to build the products with intuition. And coming to technologies, I think it's easier to get deeper into them and just look for the impact and gradually, uh, build product meeting the required need for my customer. So in this talk, I'm going to share how to scale multimodal LLM, and I'm going to basically dive it more from an intuition perspective. Of course, we can do the math and all, but I'm just trying to align the approach the LLMs are heading towards from multimodal perspective and how exactly it maps with the user experiences going forward. And I believe scaling is not just about using a lot of GPUs, but it's more about the performance in a balanced way. And we are not going to look at size, but we are going to explore the capabilities the multimodal will help us doing. It's more about the magic it would be creating. And I believe it's going to be extremely powerful going forward. So let's try to understand how can we get there. Um, so yesterday, actually it was not yesterday, and on a Sunday, I was in a park and I saw this bird, and it was a beautiful bird. I took a picture, and I was wondering what bird is this. So I just shared the picture with GPT, and it ChatGPT. So it just showed me the name of the bird and what exactly. So it's fun to explore the possibilities the the AI is giving us today to look at things. And I believe multimodal is going to be a game changer. Um, I follow Andrej Karpathy a lot. He has been doing a lot of exciting stuff. And you can also look at his GitHub repositories in terms of optimizing LLMs, inferencing, the libraries he has created. And this is what he also thinks about it in terms of multimodal. And it's basically the future of computing uh, going forward. We will forget about computers, I'm sure, and we'll be just looking at multimodals. Um, I think so. I also came across this interesting message by Tim Cook, and he thinks the future is actually multimodal computing. Um, it's basically the traditional computers, they won't be existing, and then individual users will be just using the multimodal LLMs. So the doubt basically I had when I was exploring and diving a bit deeper around multimodal was what is the difference, or is it the same as the diffusion models? We have heard a lot about stable diffusion and Midjourney and DALI. So in the next slide, I'm going to just dive a bit deeper and come up with a difference. So uh, basically, diffusion models are very different from multimodal models, and what difference we can see is that multimodal models are stemming more from large language models, which are transformer architecture based. And they are using the autoregressive encoders, which is basically predicting the next component. And From a series of these time steps, it kind of predicts what is coming next compared to what diffusion models are. So diffusion models are more like denoising. It basically predicts the next pixel, whatever is, So it is not something which is happening at a related way. It is happening more like a creative way. So whatever comes next, it just shows up. And thereby it makes it faster compared to the transformer models, because transformer models are more like logical and they need to process a sequence before coming to a, um, a response to a query. So, for example, the transformer models, what we see is GPT. The original DAL-E was also actually a transformer model. But in terms of diffusion, we know it's DALI or it's Midjourney. So those kind of models. So this kind of a thinking actually made me think that this is how actually our brain works. Our right side of the brain is more creative. Um, you basically, just imagine, and you don't have as such a pattern to follow compared to what our left brain is. It's more logical, more to process. So I just thought maybe, the left brain is actually more like the transformer versus the right brain is more like a diffusion. Just wanted to share everyone with my perspective on this. Um, so before we dive a bit deeper into multimodal models, I also thought of, just taking a step back and looking what all architectures are there besides the multimodal and besides the transformer architecture, sorry. And those are basically the non-transformer based. And the one which was much before the transformer architecture was discovered was the RNN, which is the recurrent neural network. And it's a class of neural network which we are able to handle sequentially. It's comparatively slower because it takes one input at a time, and hence it was not that scalable. However, transformers, they let us do parallel processing, and they enable more, efficient training and inference compared to the RNNs, what we just saw. So transformers were preferred because they lead to a faster computation, better scalability, and of course, the ability of getting trained in parallel compared to the RNNs. There was also an architecture which was introduced after Transformer, which is Mamba. Mamba is again a new architecture for large models, and it kind of uses the structured state sequence, which is basically about managing more lengthy data sequences. Um, so it kind of works like RNN in terms of, uh, getting incorporating stuff or sequential data one by one compared to the original RNN model. But it also lets you handle a lot of, computational data and training comparatively. So more like a structured approach to RNN, you can say. This also has, I mean, Mambas is actually one more like convolutional neural network, which is also known as CNN. And it's a class again of deep neural networks. And basically, it was there was this company by the name called as A121 Labs. Not sure if you've heard of. So they came up with Jamba, an architecture, which is kind of a mix of Mamba, transformers, and mixture of experts. It's been quite recent, and there we see the amalgamation of all these architectures, and they are trying to take out the best of all these three. And by adding vision to Jamba, there is a model called as S4ND. So S4 is what we just, learned about the structured state space sequences, and ND is basically n dimensions. So um, multimodal is about multiple dimensions, multiple modalities. So that's what the uh, S4ND is aiming at. And it basically comes with vision capability. So this could be an alternative path to creating multimodals, which is non-transformer. And the good side of it is that it needs lesser GPUs and it needs higher throughput compared to the compute power. But transformers are still preferred. There is a lot of work still that needs to happen around these architectures. Um, right. So, sorry. Um, so what we'll see now is that I mean, I came across this interesting timeline that LLMs actually are going to be by default as multimodals, and we can see in 2022, DeepMind came up with Flamingo. And since Flamingo, there has been an uprise, and we have been seeing a lot of multimodals coming up. So it's just like, we had a phone back then, which was gradually, we saw smartphones coming in, and then there was this camera. So it's just the same way these large models are actually, incorporating the multimodal nature. So that's what we'll only see going forward. Uh, Sorry. So, uh, by diving a bit deeper into multimodals, what I realized was that multimodals are not very different from large language models. And they are just about adding some additional capability to the language models. And additional capability is more like something which is close to human senses, such as vision, um, the touch, whatever sensories a human being is capable of. So adding those additional capabilities makes the large language model as a multimodal model, and it is achieved by an encoder, which is actually a neural network framework called as CLIP, and it is a contrastive language image pre-training uh, framework, which is actually a neural network, and it is kind of built for training on a variety of images, text, and all those things. So it is kind of it is basically natural language only, but it can predict texts, it can predict images, and I mean that's how basically it is supposed to do. So using a clip encoder, it can generate the embeddings and the texts and all. So the point to actually note here is that uh, when you add modalities to a large language model is that you just add layers. You don't touch the existing layers, you just add the layers and train only those new layers uh, in terms of images, in terms of text. And the training is basically a joint training, like you can see in the image. So if there is an image of a dog, there's a description next to it. Similarly, if there is a cat, there's a description next to it. So this is called as joint training. And I mean, it depends. I mean, on what your requirement is, but it only applies to the new layers which have been introduced as a part of the other modalities besides the text-only language model. And for any framework like this to test the similarity, how basically the consensus is reached. Okay, this is what the response should be. There is one of the measurements is cosine similarity, and it's basically measured. It basically uses the fundamental principle of cosine, which is just an angle between two vectors, and whatever is the closest one, it points in that direction and then gives us the response in that direction. Um, so, I mean, some of the learnings we have had is, what really works or what makes multimodals is good that, um, like we have seen, it is not just limiting to single modality. So it kind of breaks the monomodality aspect and introduces modalities in different directions. Um, and a first step towards this was taken last year by Meta, and they introduced a multimodal model called as image bind. Um, and image bind is it's a model which learns from single embedding, and if you can see that this is a picture which I basically picked up from their uh, uh, article, and how they are trying to basically cross-train by introducing the image, the text, the audio. So, for example, you see a bird chirping. As a human, you can see it's if it's a toy bird which is making a noise or a bird sitting in a tree making a noise, so you can differentiate that. The machine was not able to, but with these kind of exercises, especially with image bind, these kind of challenges have been addressed. So what I felt was, and I feel still now, is the biggest challenge in terms of heading towards multimodal and making it very close to human experience is the lack of awareness. And I think that by introducing these, additional sensories such as depth, thermal, or the the infrared radiation and all those things, it will actually gradually head towards that aspect where the machines get very closer in terms of, because what the machines and what humans lack is the awareness. So I think that would actually lead toward making that achievable going forward. So I mean, image binding shows that it's possible uh, to kind of create that kind of space with the multiple modalities. And recently, I think it's not recent, but some time back, Panda GPT actually used image bind too. So they were just instruction based, and they have now tried to combine the language model Vicona from a vision perspective. So now Panda GPT is also, well skilled in terms of text and image kind of pairing. A step ahead, which is very exciting recently, in fact, just a month or 2 months back, EPFL and Apple came up with a joint research, and the research's aim is to basically giving vision capabilities to a large language model. And the paper they have published, it's basically doing trained joint training and um, I mean, they're actually making it very much left brain, uh, what we saw in the picture a few slides back. And in terms of really understanding what the machine is saying. So, for example, the awareness aspect, which I was mentioning about. So, it's really seeing if it's a bird or a toy bird making that noise. And it's a framework they have built called as 4M, which is massively multimodal mask modeling. And it basically creates a model that can understand and generate an array of vast modalities, right from texts to images to geometric and semantic data. And this has also been, achieved by joint embedding. And a point to note is that even the output is actually also joint. So whatever responses you see, they all come um, as the training or as the embeddings have been done around that. Um, and this is again a transformer based. The earlier approaches, what we saw was just using a autoregressive encoder. Here in this case, it's using the encoder and decoder uh, at the same time, and it's across diverse images, diverse, I mean, data, whatever is, network feature maps or whatever is there, and they are basically sequenced into discrete tokens. These are tokenized, all these modalities, because it's encoding and decoding. So it's all sequences of these tokens. And um, okay, so what else should I be talking about here? Okay, so as you can see the image, so the image in the previous modalities where it was just image and text, the vision based, they were looking at just the RGB values. But now you can just go beyond the RGB values. You can look at the shape, the edges, the basically the geometric structure of that, the feature maps. So all those things are actually unifying together to present this kind of a model. Um, Now we have seen till now, how exactly multimodal is created and what basically goes in terms of creating multimodals. Um, if we want to, build a use case such as semantic search or recommendation engines using multimodals, uh, we could actually use RAG on top of it. So, I mean, using RAG for multimodals is, I'll be kind of talking about two primary ways of doing it, but a very standard way of using any RAG is you basically download images or text, and you just try to build a vector for text separately, and then you create a separate embedding using clip, probably what we just saw. And then, you kind of retrieve the data and the LLM generates response. But Specific to retrieving for multimodals, I mean, there are two methods we can look at. Uh, One is use a multimodal embedding model to embed both text and images. And I mean, here we could basically use the image bind, for example, multimodal, in this case, can be image bind. And for the second one, it's the use a multimodal LLM to summarize images. Now, this is a bit challenging. Uh, it may need some extra work because you first need to summarize, and then you can basically embed that summarization. So you need to parse the summaries and the text data. And to do that, you can use OpenAI's text embedding 3 small um, model to that. And and basically, I mean, basically, how does the summarization work is, I mean, one way is that you could encode that in a base 64 kind of an encoding and then send that encoding. Uh, or, I mean, the standard embedding, which happens using the clip way. So these are the ways, basically, you could look at retrieving um, the method. I mean, these are the retrieval methods for multimodals. And so I'm going to quickly talk about uh, the ways we can, improvise the performance of the LLM. So whatever applies to LLMs also applies to multimodals because, as we discussed, multimodals are an additional capability which sits kind of on top of LLMs. And we all know about flash attention. And flash attention has been there for some time, and we have been using that to inference a lot of models. Recently, there has been a reduction of flash attention too, which happens to be faster than flash attention. And faster also means that it has now a capacity of taking a longer context length. So earlier it was 8K, but now it can take up to 16K. And I mean, it works better when it comes to understanding larger data, high resolution images or videos and audios and those kind of things. So, and it has been noted that when flash attention has been applied to models for inferencing or fine tuning or training, there has been a 72% higher utilization compared to the previous utilization at a flops level. So why it is doing that is because it's minimizing the non-matrix calculations. So typically the cores in the GPU are focused on the matrix multiplications, and when you remove the non-matrix part of within the algorithm, then the GPUs can just focus on the matrix multiplications, and that kind of increases the efficiency of processing. And so now that so this the speed kind of works well from this perspective. And sorry. Okay, yeah, the other one. So now that we have spoken about flash attention, which we are all aware of, there has been a lot of more research happening on how to speed up transformers in a I mean, what can be the other ways besides what we have seen? So, I mean, we have spoken about autoregressive decoding at the beginning, which is principal to the encoding method for multimodals. There has been a lot of exploration, and uh, to improve the performance and the challenging, nature of these LLMs in terms of performance. Sometimes the decoding method could take some time, and there has been introduction of a lot of algorithms, and the two prominent ones which have come up is the speculative decoding, which kind of is like guess and verify approach. So it's like us. So for example, if any one of us, as a human, you think about if you're getting questioned and you have something which you have read in the past, but you try to recall and just try to propose to an audience and which may work out to be like that. So speculative decoding, it matches to that kind of behavior. So that approach was proposed, but that approach was also like, taking some times in predicting, because guess and verify kind of breaks in two steps. So first you guess. So the guessing creates a preliminary model, and then you do the verification pass. So the verification part means that LLM needs to be smart enough to verify that part. So there was an extra effort in terms of training and focusing on that part. So this actually kind of challenge led to the introduction of more precise decoding, which is called as look ahead decoding. And look ahead decoding, I mean, the fundamental thing about is that it generates multiple tokens, um, and more like, it kind of generates concurrent ones, and it's using the n-gram thing, which is basically an n-gram is a sequence of it's a part of linear algebra, so it's more like representation of a sequence in a particular order, one after the other. And the symbols can be anything. It can be letters. It can be, um, I mean, it can basically be anything in a particular order. So, so this is basically kind of utilizing a method that enables parallel decoding, and so the verification happens while the parallel decoding is happening, and the sequence also keeps getting arranged. So the picture, what you can see is where um, the n-gram pool is used for the parallel processing. Um, so basically, it works well for scenarios where latency is very important, and for GPUs to squeeze the maximum performance from GPUs, this algorithm is supposed to be working well. So such as A100s or H100s, and the new GPUs coming forward. So this is what the other methods are in terms of speeding up the transformer performance. Um, I just wanted to also talk about, at some point we all want to run LLMs, and from my experience, when you run LLMs on a multiple GPU, it kind of, um, it isn't straightforward, but from my experience, by integrating a lot of libraries, it kind of gets effective and exactly making meet what we are looking for. So I tried running a big model, a very big model, such as Snowflake's Arctic, which is 479 billion parameters. It's a mixture of experts, and using flash attention and using a deep speed library to kind of quantize it to FP8. So, I mean, when you quantize for efficient inference to the low bit integers, it kind of works on reducing the precision, and so I mean it works well. I mean, in terms of generating the desired data, it works for SQL queries and all the way it is supposed to generate the data. So so this was basically run on one of our Ori's 8 H100 bare metals. And the challenge was to also make all the GPUs communicate. And over the time, it was realized that it needs an NVIDIA Fabric Manager. It's a library that works on these A100s and H100s primarily because these are data center grade GPUs. And to kind of manage the communication and the connectivity amongst these GPUs or across a network of these kind of GPUs, this library plays a very crucial role. So I just wanted to share my quick experience in terms of running such large model. Um, this is my last slide, and I have just a few recommendations for people in case they are looking to pick up some work or explore some projects. So, I mean, the everything is moving towards multimodal, so it's just good to focus as a skill set towards multimodal LLMs, and you could basically start with I mean, looking at diffusion models, you can you can basically add rag to them, you can edit them, and you can fine tune them using the 4M framework. You can look at the one of the latest multimodal models, the COG PLLM, and it's an interesting model to consider. Um, it kind of supports very high resolution images, and so that is one model you can, look at. And I think it will be very interesting to also explore the 4M from a fine-tuning perspective. Um, and you can also leverage the image bind, so whatever, few frameworks and libraries and models we have visited. So those kind of use cases we could build using RAG as well. So this is my experience. I just wanted to share. Let me know if you have any questions.
Yeah, thank you so much. Really enjoyed the talk, and it's interesting. We're on kind of a similar wavelength because my talk is going to be dealing specifically with embeddings, and I'm going to go a little bit deeper on clip and on image bind and actually show hands-on what we could do with those embeddings. So stick around for that if you're interested in learning more. It's actually a talk that I gave at CVPR, an extended version of that talk. Neha, you got some wonderful questions here in the Q&A. I just want to be kind of mindful of time. If you want to pick maybe at most 3 questions to answer live, and the rest, if you wouldn't mind, just answering kind of uh, uh,
Sure.
asynchronously, or
Um,
type out the answer. I'll let you choose which ones you want to answer.
okay, so I'm just looking from the bottom. Yeah, I'm happy to share the presentation after this. So how do joint embeddings work concurrently? Okay, so my presentation actually has links to the papers, which kind of dives us deeper into how exactly it works. So I guess, Adam, you can look at that from a deeper dive perspective, um,
Oh, Neha,
because
I
I'm
should
just going to
say,
be high level.
I should say, make sure you're looking at the actual QA section, not the chat. So on the three uh, dots, I'll say more, then you'll
Oh, okay,
see
so
a QA.
sorry. I'm so
Yeah.
sorry.
No worries,
Yeah,
no
yeah.
worries. It's just for easier management for you. Yeah.
Yeah, yeah, yeah. Uh, okay, so Harcharan, I'm so sorry. Actually, I haven't explored yet the observability framework for the LLMs, but so observability can be, perceived in two ways. So one is the observability in terms of the quality, and the other one is in terms of the hardware utilization. So if you're looking at a framework from that perspective, the throughput of the tokens and all those things, then you can, I'll actually point you to the GitHub repository we have, which we have built in-house. It's called Befori, which is basically benchmarking your LLMs on GPUs, what we have. So you can actually go through that repository. So I'm happy to point you to that repository for performance. Let me know if I've answered it correctly. Otherwise, feel free to reach out to me.
And
Um,
I'll add to that actually. Another good framework is just Langsmith, because Langsmith will trace all the calls you send to whatever LLM provider, and it'll get you all like it'll manage the input, output, and all that other stuff. So definitely, Langsmith is a good tool.
so Mohammed is asking how much does CPU impacts the performance on deploying the large language models. So Mohammed, a lot of models we see now are also getting CPU friendly. Those models can execute both on CPU and GPU. Of course, they would have their own limitations, but if you go through any model's GitHub repository, it will have ways of, passing the flags, which basically makes it GPU only and CPU only kind of. If you have both a neural engine plus a GPU, how can you make use of both? Okay, sorry, Jim. This is a bit new to me, but I'm happy to dive a bit deeper into this GPU neural engine. Or Harpreet, if you know an answer to this, I'm happy to know.
Yeah, if you're talking about neural engine from like Intel, like their NPU, I'm exploring those right now, so I don't have an answer for that. Um,
Okay.
but
Yeah,
I
but
do
this
want to
is
say
interesting.
we should probably keep it moving to Dan's presentation. But Ganesh, Harcharan, D, and Vithal, actually, your questions are very relevant to my presentation. I might actually answer them through the course of my presentation, and if not, I will answer them uh, afterwards, after my presentation. So feel free to stick around.